Our two last topics for this chapter, Gauss's law for magnetism and an understanding of permanent magnets with a focus on ferromagnetism. First, we'll get started with Gauss's law for magnetism. Remember that flux is the integral of E dot dA for electric flux. We're integrating E dot dA over a surface. And we can do the same thing for a magnetic field and get the magnetic flux through that surface. The integral of B dot dA. Gauss's law followed from the fact that electric fields originate on positive charges, terminate on negative charges. So I can draw some kind of a surface here where I have a net flux into or out of that surface. And the flux then would be proportional to the amount of charge enclosed. That's Gauss's law. The flux is proportional to the charge inside of our Gaussian surface. Let's take a look at what happens when we talk about magnetic fields. Magnetic field lines always close on themselves. They form closed loops, as we see in this image. So if I draw some kind of a enclosed Gaussian shape, every magnetic field line entering also exits at some point. So there's no net flux through this surface. That gives us a Gauss's law for magnetism that looks like this. The integral of B dot dA around an enclosed surface is equal to 0. And that's because we cannot isolate a north pole or a south pole. They always come as a pair. We like to say there are no magnetic monopoles. You cannot find just a north pole or a south pole by themselves. There are no monopoles. They always come as a pair. So Gauss's law for magnetism, the fact that there are no magnetic monopoles, or another way of saying that, the integral of B dot dA around an enclosed surface is 0, is really a result of observation. Let's talk about permanent magnets. And the most common type are ferromagnetic materials or iron-like materials. Iron atoms act like little tiny bar magnets. Every iron atom has a magnetic moment. And as the iron forms into a solid piece of iron, the magnetic moments align with each other because that's what little magnets want to do. They want to align with the magnets they're next to. But what happens is they start to align in one area in one orientation and in another area in a different orientation, and we end up with something that looks like this. As the iron was forming into a solid, the magnetic moments of the iron atoms align next to each other, forming a permanent magnet in this little region right here. And I'll draw a little symbol for a magnet, the arrow being the north end of the magnet and the tail of the arrow being the south end of the magnet. But the region right next to it formed with its magnetic alignment in a different direction. And a region over here points in another direction. Because the domains are all randomly aligned, this piece of iron does not act like a permanent magnet. Each little domain, we call these little regions domains, each little domain acts like a permanent magnet. But because they're all randomly oriented, you put them all together and their effects cancel each other out, the fields cancel out, and you're left with no net magnetic moment for this iron block. If we take this iron block and put it into an external magnetic field, these domains tend to align with the field. So there's my iron block, and I've got a strong external field that points in this direction. And what happens is some of these domains twist, or they feel a torque because of this external field, and they try to align themselves with the field. Now, if you look at this block of iron, the domains have a net alignment. And so this block of iron now, it has an overall magnetic moment with a north end on one side and a south end on the other side. If we remove this external field, many of the domains will stay in the alignment they had with the field on, and we will have a permanent magnet. If you bump the magnet, drop it, sometimes those domains will go back to their original place. They'll go out of alignment, and you'll lose some of the magnetism in the bar magnet. So you have to be careful with your permanent magnets. Oftentimes, when this happens, you can remagnetize the magnet by putting it into a strong magnetic field. Let's take a look at how we do that in our lab. One application is in the use of electromagnets. An electromagnet, remember, we can turn the current on and off, so we can turn our magnetic field on and off. Oftentimes, it's a solenoid like I've drawn on the left here. You run the current through the solenoid like this, and you get a magnetic field. The one on the right has an iron core on the inside. It's a piece of iron. When you run the current through the solenoid, it forms this magnetic field just like the one on the left does. But when that field forms, the magnetic domains in that iron core go into alignment, and we get some extra magnetic field due to the alignment of those domains. And so the net magnetic field in the region below the magnet is greater when there's an iron core inside the electromagnet than it would be if there was no iron core. It's a way of intensifying the magnetic field in an electromagnet. So you're wondering where this magnetism comes from in a permanent magnet. I've mentioned that an iron atom, there are others also, but iron is the most common, acts like a little tiny magnet. That's probably due to the electrons. There's a cloud of electrons around the outside of the atom. There might be some net movement of charge in that electron cloud that's creating a magnetic moment. And each electron acts like a little tiny magnet also. So a combination of these things gives the iron atom its magnetic moment. We have a model that we use, and models are not always correct, but if they're useful, that's the important thing. It gives you an idea of how something might happen, or a way of thinking about it, even if it's not technically correct. And one model for the magnetism of an electron is to view it like a little ball of charge spinning like a top or like the Earth on an axis. You could imagine if there was a little ball of charge spinning on its axis like a top, that charge moving in a circular path would be like a current loop. And a current loop acts like a magnet, a little magnet with a north pole and a south pole. But electrons are not little balls of charge, and they don't spin like a top. So this analogy falls apart very quickly. But it might help you in some ways imagining how an electron might have a magnetic moment. We've discussed magnetizing a piece of iron. You put it into a strong magnetic field, remove that field, some of the domains stay in alignment, and you have a permanent magnet. A visual way of representing that is a graph like this. We're going to graph the applied magnetic field on the horizontal axis and the total measured magnetic field on the vertical axis. So if there was no iron present, if we just had our test chamber and we turned on a magnetic field, we would measure that much magnetic field. We would get a graph that looks like this. If there was no iron present, we just measure whatever field we turn on. But if we put a chunk of iron into this region of space and we turn on this external field, the domains in the iron will align and add or intensify that magnetic field. So our graph will look something like this. We get more magnetic field than we are applying because the domains are aligning and we're measuring a stronger field because of the effect of the iron. Now we remove this external field, and some of the domains in that piece of iron will stay aligned, and we will have a permanent magnet, which means we're going to measure some magnetic field even though we're not applying a magnetic field anymore. This is called hysteresis, when you go through a cycle and you don't come back to where you started. So we've gone through a cycle, we've turned on an external magnetic field, we've turned it off, and we're not back where we started. We now have residual magnetism because we've created a permanent magnet. Now, what if we have a material and we want to demagnetize it? So we're starting with a permanent magnet. We're starting on this red dot. We have no applied external field, but we're measuring a magnetic field because we have a permanent magnet sitting there, and we want to demagnetize it. One way is to turn on a strong magnetic field and get the domains to align in that direction. Once you have the domains aligned, you have a permanent magnet. Now we reverse our magnetic field, but we reduce the intensity of the field a little bit. So we get it to go in the opposite direction, but a little bit weaker field doesn't flip as many domains. So we left some of the domains in the other orientation and we flipped some of them. Now we flip our field again, but we reduce the intensity again. So we leave some of the domains in the original orientation, in this orientation, and we flip some. And we keep flipping our field, our external field, back and forth and reducing the strength each time. So every time it causes domains in our piece of iron to flip, we're leaving some behind. We cause a whole bunch to flip. Then we cause, let's say we cause 10 to flip this way. Then we cause 8 to flip this way. Then we cause 6 to flip this way. Then we cause 4 to flip that way. Each time we reduce the number that flip. And when we're all done, what are we left with? Randomly oriented domains, no permanent magnetism. In the old days when we had CRT TVs, cathode ray tube televisions, They were really deep because you were shooting an electron towards the screen. If this was the screen of the TV and you turn and look sideways, they're very deep because an electron gets shot towards the screen and has to hit the part of the screen to make it fluoresce, so you see it light up. Well, if your kid was playing with a magnet near the front of the TV and accidentally induced some magnetism to the screen, that would mess with the path the electron had. So you'd have a spot on your TV that was never right because the electrons got deflected and hit the wrong place. Your picture was distorted. So you would have to demagnetize the screen. You could buy a coil and run it over the screen and demagnetize your screen. And here's an image of a submarine degaussing station. Because our submarines sit in the magnetic field of the Earth for long periods of time, often in one orientation, they'll pick up a magnetic moment, which makes them more easily detectable. So periodically, they bring them into these submarine degaussing stations. You can see it's a coil of wire. It looks kind of like a solenoid, doesn't it? We can only see the part that's above the water here, but it runs around below the water also. They bring the submarine into the middle of this solenoid, and they can turn the current on, make the magnetic field go one way and then the other way, and degauss the submarine that way.